Thanks to the organizers for having me here. It's a pleasure. Very interesting conference and beautiful environment. So what I'm going to talk about today are some recent results that stem from the observation that recently there are two notions of quantum space-time that are emerging. Well, one is not that recent and is what you all have heard about already, so it's noncommutative space-time. And the idea of a noncommutative space-time is that noncommutativity is a way to encode possible limitations in the localizability of space-time points. In general, well, you have all seen this. We can write the commutator between space-time coordinates, for example, as a power series in some constant L, which is the quantization parameter. This parameter is in principle independent from h bar, so quantization of space-time is independent of on the quantization of phase space. In fact, if one wants to extend this to fully non-commutative phase spaces, this can be a non-trivial matter. We have discussed this in a recent paper with Fedele, Patrizia, and Javier. Besides this, there is, this kind of quantum space-time has attracted attention within the context of quantum gravity. Besides this, more recently, there is another notion of some sort of quantum space-time that has emerged in the context of research on quantum information. So in this case, you are within standard quantum mechanics, and you ask yourself what happens if the reference frame that you are using to describe properties of your quantum system has quantum properties itself. So what you are doing is you are separating your system into two parts. One part is playing the role of reference frame, and it will have some non-commutative phase space. And the other part is the quantum system that you are describing, and it has its own non-commutative phase space. Notice that here I'm using two different constants. One is h bar and one is kappa. Of course, we expect that the two constants are h bar because we are in quantum mechanics. I'm just keeping them formally different because we are going to be interested in what happens when just the reference frame is quantum. So I want to have a different constant here so that I can play with it. But we expect it to be the Planck constant as usual. So if you're associating a reference frame to a quantum system, in some sense, which we are hoping to clarify during the talk, you are assigning quantum properties to space-time itself, or at least to the way you describe the space-time properties of the quantum system that you are studying. So this is a very different scenario from the one of non-commutative space-time, and first of all, because here we need to talk about quantum matter, while in the quantum space-time picture you are just talking about space-time. You're not necessarily putting matter in it. Well, at some point, yes, but the formalism doesn't require you to, while here you have quantum matter with quantum properties. And also here, this sort of quantization of space-time that you hope to achieve is governed by the quantization in phase space. And now the question is, are these two concepts related, at least in some limit? Can we put these two formalisms in contact? So this is the question that I've been trying to answer in collaboration with Angel Ballesteros in Burgos and Flaminia Giacomini in Zurich. And in the last paper, also Diego Fernandez Silvestre, also in Burgos. So the discussion is a two-step process. So first of all, and this was discussed in this paper, we want to identify what transformations are described by this change of quantum reference frame, okay, so within the quantum mechanical context. And what we found is that when you transform between quantum reference frames, you find a group structure, which of course is not the Galilean group structure that you would have in standard quantum mechanics, but it is still a finite dimensional algebra that has 7 generators. So we call it D7. And of course, this algebra reduces to the standard Galilean algebra of quantum mechanics when, well, here I should have put kappa. So kappa is the non-commutativity of the reference frame. So you reduce to the standard Galilean algebra when the reference frame is a classical system, as is the case in usual quantum mechanics. Then the second step is, having found this group structure, is this group structure connected to quantum groups? Because we know that quantum groups are a good way to describe symmetries of non-commutative space-time. And in fact, and so we study the Galilean quantum group, because we are generalizing a system with Galilean symmetries. And in fact, we were able to find that there is a correspondence between these quantum reference frame transformations that are described by this 7-dimensional algebra and a specific quantum deformation of the Galilei group that in particular has a commutative time, because in quantum mechanics that's what you have, and we wanted to keep this property. So this is what I am going to discuss in the rest of the talk, but I wanted to give you what is the outline so that it is easier to follow. Okay, so let me start with one preliminary slide, which is standard 1+1 dimensional Galilei group. So from now on, we are only going to work in 1+1 dimensions. So this is very standard. You have 4 generators, which is boost, time translation, space translation, and then you have the central element M. These are the generators of the algebra. Then you build the group by exponentiation, and using some commutative, of course, group coordinates theta, b, a, and v. So these are the parameters of your finite transformations. And since this is a group, you have to satisfy a number of properties, namely the group law, which gives you a consistency relation between the algebra of the generators and the group law of the group coordinates. And also you can represent your group on the phase space of a quantum particle, like so. So this is all standard, but I wanted to fix notation for later. Then let's go to quantum reference frame a bit more in detail. So for the discussion, we are just going to consider 3 quantum particles and consider that, for example, particle C is a reference frame, and you're describing coordinates and momenta of the other 2 particles with respect to the particle C. This means that the phase space of particle A and particle B will be the phase space coordinates as seen by C. And what is a quantum reference frame transformation is a map that maps the quantum state that is defined in the Hilbert space of A and B relative to C to the quantum space that is defined in the Hilbert space of B and C relative to A. So we are changing from having the reference frame of it identified by particle C to the reference frame identified by particle A. And then you can easily realize that if particle A is in a quantum state, then the transformation parameters that transform from the reference frame of C to the reference frame of A cannot be just simple numbers, commutative numbers, because, for example, if particle A is in a delocalized state in position, then you do not have a number that allows you to transform to that frame. You will have to have some operator that plays the role of transformation parameter. So what happens is that, so for example, here I am writing the translation transformation and the boost transformation. What happens is that in your exponential, the parameter that you have here now is an operator. For translation is the operator relative to the coordinate of A, and for the boost is the operator relative to the velocity of A, so P over m, the mass of the particle. And once I write it in this form, you already start to see some similarity with the quantum group structures, because that is what a quantum group is some object with the non-commutativity of the parameters and of the operators. But I mean, at the moment, this is just some interesting formal similarity. We want to understand if there is something more to that. So once we have defined these kind of transformations, then, for example, we can study how they act on the phase space coordinates of particle A and of particle B. At this point, you're not just acting on the particle B, but because you have transformation parameters that are operators, you also have a transformation of the coordinates of the reference frame you are transforming to. For example, and here you can see the action of translation and of boost, and you see that in the limit of kappa that goes to 0, which is the limit where your particle A is completely classical, so you have a classical reference frame, then you are reducing to the usual transformation induced by the Galilei group on the phase space of particle B. Once you turn on the parameter kappa, then you have a deformation. And now we want to, so the first step is to investigate what are the group properties identified by these kind of transformations. And to do so, we look at the operators that are basically the exponentials appearing in our U, the unitary operators that generate the transformation. Of course, these operators here are operators that act on the tensor product of the phase space of particle A and the phase space of particle B. This is why I'm putting here this tensor product symbol. So what is on the left acts on particle A and what is on the right acts on particle B. So starting from these two operators, one can show that by completing the commutators, there is a 7-dimensional algebra, which is what I was mentioning before, that they close. So you have the two operators of translation and boost, and then you have some additional operators, which I will explain in a second here. So to understand them, we look at the action of all these operators on phase space, and it turns out that the two operators dA and dB are basically generating dilations on phase space, either of particle A or of particle B. Then the two additional operators QA and QB are basically generating the motion of a free particle. Okay, so they are related to the free particle Hamiltonian. And then the operator T is just an operator that lets you evolve in time the space coordinates without touching the phase coordinate. And what is interesting is that these operators, they can just be derived by asking that these two are closing some algebra. But then they found a physical meaning also from the point of view of quantum reference frame transformations. In fact, in previous literature, these operators had already been introduced when people were asking that quantum reference frame transformations were symmetry, extended symmetries of the Hamiltonian of the quantum system. So we have, it is nice because we find we found a mathematical result that had already been derived from physical reasoning before, so it gives us a consistent picture. So this is what we know about quantum reference frame transformations. Now we want to understand the connection with quantum groups. Just here a brief reminder about quantum groups. So they are basically a non-commutative version of the exponential map of an algebra. In this case, we are interested in the quantum deformation of the Galilei group with central extension. So what we do is we introduce the group coordinates as non-commutative operators. Their commutators are ruled by some parameter, which is a quantum deformation parameter, which we call alpha. And notice that when we are working just at the level of quantum groups, this parameter alpha, as I said before, is not related to Planck constant or anything. It's just a parameter that tells you how the group is deformed. This same parameter governs possible deformations of the group law and possible deformations of the algebra of the generators. Of course, all these deformations have to match, they have to satisfy some consistency conditions so that you get a proper quantum group. And in particular, for the Galilei group, it has been shown in these papers that you have 26 inequivalent quantum group structures that can deform the Galilei group into a quantum group. And we have to pick one to see if we can make a connection to the quantum reference frame description that I just discussed. So the two immediate conditions that one may want to impose are, well, first of all, that B, which is the parameter associated to time translations, is commutative, because we want to reproduce commutativity of time in quantum mechanics. And also we ask that the parameters A and B, which are the parameters of translation and boost, do not commute one with each other. And this comes from the fact that when we were writing the quantum reference frame transformation for translation and boost, we had these two transformation parameters, and we know that they do not commute because they are coordinates on the phase space of a quantum particle. So we want to also keep this property. And interestingly, these two conditions allow us to select just one among these 26 possible realizations of the Galilei group. So this is what we are going to work with in the following. And here I show you what this, which one is this Galilei group. To do so, in fact, we start with the corresponding Poissonly group, which is just the limit of the quantum group with commutative parameters here. Commutative parameters, but with non-trivial Poisson brackets, so dynamical parameters. This is just standard Poissonly groups. And we look for the properties that I just mentioned, and we find that this is the algebra of the transformation parameters that satisfies our conditions. You see that B is commutative, and A and B do not commute. Then you can quantize it and obtain your quantum group. And when we quantize, we transform the Poisson brackets into commutators. But instead of using the constant h bar in our quantization, we use the constant kappa, okay, which is the one that we already had introduced before. And we do this because this will allow us to find better the correspondence between the quantum group and the quantum reference frame transformation. So this is the algebra of transformation parameters. These parameters have a non-deformed group law, so they work as the standard Galilei transformation parameters. However, the algebra of the generators also is deformed in this way, And you see that here we have both the alpha parameter, which is the quantum deformation parameter, which basically is the parameter that governs the non-triviality of the Poisson brackets of the transformation generators. Then we have the parameter kappa. Kappa is the parameter governing the quantization of the algebra of the transformation parameters, okay? And then we have h bar, and h bar is the usual h bar that governs the quantization of the phase space on which the Galilei generators are acting, okay? So there are three parameters in this model that we can work with. And when we establish the correspondence with the quantum reference frame transformations, we will have a more physical understanding of the meaning of these parameters. Here we didn't look, I mean, we didn't care about the coproduct. We were only looking at the algebra side of the structure. For the coalgebra, we still didn't, we didn't work with it because we couldn't, it was not relevant for finding the correspondence with the quantum reference frame transformation. In future work, of course, that is one of the things that we need to understand, what happens to the coalgebra structure and how we can interpret it in this framework. But for the moment, we are only working with the part of the algebra, okay? So this is, I'm telling you the story up to where we are now, but this is, there is much more to understand. To start getting to this physical interpretation that I mentioned, so we remember that in the quantum reference frame approach, we had two phase spaces, one for the particle that is being transformed and one for the particle that is playing the role of reference frame. And they have, just formally, we gave them different quantization constants. And we want to see whether we can realize our quantum group on a similar phase space. And to do so, we represent the group coordinates on the phase space A, and this is what we find. And you see that we only have, so we have phi, which is a free parameter that has dimensions of velocity, and then we have two more parameters, delta and gamma, that have just the meaning of labeling the representation that we are using for the parameters. And then we represent the generators, M, P0, P1, and K, on the other phase space, so on the phase space B. And this is what we find. Notice that also here we have some, we have a free parameter, which is psi, that appears in the representation of P0. And by looking at the form of the Casimir of the algebra in this representation, one can see that this psi can basically be related to the internal energy of the system. So in the following, we will assume that we can put it to 0. Okay, having done that, we can put everything together and define these operators. Now, these operators here act on the tensor product of these two phase spaces. So what is on the left acts on phase space A, and what is on the right acts on phase space B. And we find this representation that allows us to write the operators of the quantum Galilei transformation indeed in a form that is very similar to what we had for the quantum reference frame transformation. And before going to show the actual equivalence, we need one more step, because if you just look at this representation here, in principle, you can compare it with the representation of the analogous operators that we have written for the quantum reference frame operators. And it's not particularly insightful at this level. But then what happens? That if you take your representation at the first order in the quantum deformation parameter, then this is the representation of coordinates reduces to this. And you realize that, for example, the v parameter is almost a velocity, but rescaled with this parameter phi. If we want to interpret this as a physical velocity, so something such that v times the mass of the particle is actually the momentum of the particle, we can do it if we define a renormalized momentum. So basically, we just take what is here. And then we have a parameter VA, which is the physical velocity of the particle. So what we are trying to do is to interpret the phase space as the actual phase space of a physical quantum particle, okay? Oops. So we realize that we can build something that behaves as the physical momentum, meaning that ma times v is the momentum of the particle. And moreover, we take an ansatz such that the quantum deformation parameter alpha is given by 1 over ma times phi. So it's inversely proportional to the mass of the particle that is playing the role of reference frame, okay? So what are we, just to summarize this point, what are we doing here? We are trying to establish whether there is not just formal, but also physical correspondence between the two formalisms. And the steps that we are doing in this slide are going to bring us to a perfect equivalence between the two kinds of transformation. And what is relevant here is that on the one hand, we are showing that we can interpret these abstract phase spaces on which we were representing the quantum group as phase spaces of quantum particles. On the other hand, we are showing that the quantum transformation parameter of the quantum group also can be assigned a physical meaning because it would be governed, so its magnitude would be governed by the mass of the reference frame, which is something that makes sense. And so having done this, we are ready to compare the representation in phase space of the quantum reference frame transformation operators and the quantum Galilei transformation operators. So on the top, we have these quantum Galilei transformations, where we used what I said in the first slide, and we are working at the first order in the deformation parameter, which you don't see anymore. Alpha does not appear here because we have written alpha as 1 over ma phi. And these are the quantum reference frame operators that we had defined a few slides ago. And now, if you look at these for long enough, you can realize that these operators are just linear combinations of the operators that you have below. So you have a correspondence between the two kinds of transformations. And in particular, you can write the quantum Galilei group element in terms of the generators of the quantum reference frame transformation. So this is what you have in the bottom line. You may have noticed that in the quantum Galilei group, here we only have 4 elements. However, if you look at their commutators, you will soon realize that you end up generating the other commutators, the other operators that give you the 7-dimensional algebra that we also had in a quantum reference frame setting. And so the two frameworks are completely equivalent on this algebraic level. And let me emphasize that this result is really non-trivial because a quantum group is in principle an infinite dimensional object. So it's quite interesting that if you only look at it at the first order in the quantum deformation parameter, you end up having a 7-dimensional object. And this only happens because when you represent it on the phase space, you have quadratic expressions in the phase space coordinates. So this is the main result that I wanted to discuss. I think I have some more minutes, so I wanted also to discuss what happens in the semi-classical limit. So you can look at the semi-classical limit in the two frameworks in a different way. So in the quantum reference frame setting, the semi-classical limit is just the limit where your quantum reference frame becomes a classical object, possibly with some dynamics. So you are just taking the usual semi-classical limit in the commutator of phase space. Within the quantum group approach, your semi-classical limit brings you from the quantum group to the Poissonly group, okay, which is what we had discussed before. And what I want to discuss here is that also in this limit, we can establish a correspondence between the two frameworks, and also having established this correspondence allows us to understand some things about both frameworks that we wouldn't understand if we looked at them on their own. And in particular, looking at this semi-classical limit allows us to understand what are the states of the quantum system, of the reference frame on which quantum reference frames act. So when we talk about these quantum reference frame transformations, in the beginning I said generically that the reference frame is in a quantum state. However, you may ask, does it work for any quantum state, or does it have to be a specific kind of quantum state? And it turns out that the kind of quantum state that can be used are states that are a quantum superposition of semi-classical states. And to show this quickly, okay, let's start from the quantum group, the quantum Galilei group. Oops, sorry. Quantum Galilei group acts, as we said, on the Hilbert state that is a tensor product of two Hilbert states. We can write a generic state as phi A, psi B, well, combination of objects of this kind. And the correspondence that we have found between the two frameworks tell us that we can interpret these states as the states of the quantum particle A and B, respectively. When we take the semi-classical limit, what we are doing is to take a semi-classical limit on the state of particle A. So a semi-classical state chi will be such that if we act on it with the commutator, we will get 0 with the commutator of phase space coordinates. So in this semi-classical limit, given the correspondence that we have established, quantum reference frame transformations act on states that are of this form: semi-classical state for A and the generic quantum state for B. And we can work out the action of the generators of the quantum Galilei group on these kind of states, and in fact recover what we would get if we directly used the Poissonly Galilei group. So this again is telling us that the formal picture is matching the physical picture that we have of the system. And now we ask ourselves, how do we get the quantum reference frame transformations? So not just this semi-classical version. Well, we can consider, for example, the quantum superposition of two semi-classical states for particle A. And just as an example, let's study the action of a quantum Galilei boost on this kind of state. So we act with our quantum Galilei boost operator. Because these are semi-classical states, when we act with the boost, we just get P of t over m for the first particle, and then the boost generator k acting on the state of the second particle. And then, thanks to the fact that we identified the phase space parameters of the quantum group with the phase space coordinates of the quantum particles, we can write, instead of P, we can use pi, which is the momentum of the quantum particle. And this object here is exactly, yeah, and this object here is exactly what was our boost in the quantum reference frame scenario. Notice that if instead of having a combination of two semi-classical states, I had a generic quantum state, I wouldn't be able to substitute in each of these the object pi, so I wouldn't be able to write this, I wouldn't be able to write a quantum Galilean boost as a quantum reference frame transformation. And in fact, the conjecture is that, remembering that we have shown that quantum reference frame transformations are quantum Galilei transformation taken at the first order in the quantum deformation parameter, the conjecture is that if we want to use generic quantum states for the reference frame, then we would need to use the all-order quantum group to describe such transformations. We would not be able to use the quantum reference frame formalism. And this brings me to conclusions. So just a brief summary of what we have seen in this talk. I know that there were many ingredients that not everyone is familiar with, especially for these quantum reference frames. So we have started from the observation that within quantum mechanics, one can generalize the notion of reference frame transformation if one gives quantum properties to the reference frame itself. And then one obtains these quantum reference frame transformations that have transformation parameters that are, in general, operators acting on the reference frame. We found that this transformation closes a 7-dimensional Lie algebra. And then we showed that this 7-dimensional Lie algebra can be recovered from a quantum Galilei group if we take the first order in the quantum deformation and if we identify the quantum deformation parameter with the inverse of the mass of the reference frame. And this correspondence allows us to give an interpretation to quantum group transformations. So it allows us to interpret quantum groups as transformation that act on phase space of quantum particles and that take quantum particles as reference frames themselves. And in the final part of the talk, I also showed you that this correspondence that we found allows us to give an interpretation to the quantum reference frame formalism and to establish that it works when the system that is playing the role of reference frame is in a specific kind of quantum state that is a quantum superposition of semi-classical states. And yeah, there is much more to do to understand better the whole framework, but well, I guess we can discuss during questions. Thank you.
So we have certainly a few minutes for questions, okay? So just a moment.
Hello, thanks a lot. It was very clear. I'm puzzled by this Poisson-Lie structure on the Galilean group that I don't know. So it comes out from your quantization because you impose that the bracket comes from so that the Poisson bracket comes as a limit of the
so you can see it in two ways. So either you start from the quantum group and then you can do a semi-classical limit. Your commutator becomes a Poisson bracket, so you are basically considering that the parameters of the quantum group are commutative but dynamical. And maybe I didn't understand the point.
Yeah, in fact, as you constructed, maybe I'm wrong, but you constructed the enveloping algebra, right? Because you are starting with...
I constructed, sorry?
You are starting with infinitesimal generators. You take the exponential.
Yes.
Okay.
Yeah,
so is this the enveloping algebra that you are on a classical level?
So the way we construct the exponentials to define you mean the quantum group elements, that is what you're asking?
Yeah, so
it's just, they're formally defined as power laws.
No. I mean, in the classical sense, this would be the enveloping algebra or the function ring of this group?
Yeah, it's, okay, so you are...
I think you are taking, well, maybe I'm wrong. Is it the enveloping algebra? Because if it's the enveloping algebra imposing that the Poisson bracket is equal to the Lie bracket, then you are kind of imposing a priori that it's a Poisson Lie bracket. Usually the Poisson structure exists on the dual Hopf algebra. Mm-hmm. So maybe this is related to what John was asking about the coproduct, which doesn't enter at all here.
Well, it doesn't. It's not that it does not exist. It exists. We are just not using it. I mean, we didn't study how it relates to the construction because, I mean, this was just. It was just a first step. Your question. Yeah, it's the group. I don't. Exactly. I mean, you have the. Yeah. Yeah.
Okay, so classically, what is it, this Poisson-Lie structure on the Galilean group?
Yeah.
Okay, there is certainly possibility to
need to
discuss.
This, yes.
Comment? No? Other questions? Fedele, please.
Are there great difficulties in doing it for Lorentz? So why did you, I know because you were doing quantum mechanics, but in principle the structure can be done for Lorentz without...
Yeah, in fact, I mean, one question you can ask, for example, is what is the quantum Poincaré group that leads to this quantum Galilei group? And well, the spoiler is that there is one, but this is something that is still work in progress. But yes, you can do a similar. I mean, then I'm not sure what kind of physical system you would relate it to, because here we are doing quantum mechanics. But at least at the level of the group, there is a corresponding Poincaré group, which is not the one that is related to kappa deformation, unfortunately.
So I have a follow-up question to the first question. Mm-hmm. So if I understood, so your quantization is, it's not clear if it's a Hopf algebra, right? It's just an algebra. It's not clear if there's a coproduct or...
No, they are there. I didn't show them because they were not... I mean, this is a proper quantum group and the algebra is a proper quantum algebra. I just didn't show them here because they were... I mean...
My question is this. So if you start from a Poisson-Lie group, there's this famous theorem by Etting of Kashtan that tells you can always quantize this into a Hopf algebra. Did you compare the Etting of Kashtan quantization of the Poisson-Lie group with yours?
Short answer is no. But I mean, the procedure that we followed to go from the Poisson-Lie group to the full quantum group is the one of T-matrix exponentiation.
Okay, so maybe it's the same. Yeah.
Maybe it's the same, okay. But I'm not that familiar with what you said. Okay. So I can show you the details and then you can tell me.
Okay. Thank you.
I don't see other questions, so let's thank Giulia once more.